Welcome back to the AHA method, Johnny here. Most limits are tame, push n higher and they drift somewhere obvious. Not this one. It looks like it should be 0 or 1, but the real answer is a number so famous it has no business hiding in here. Stay to the very end, too, a bonus puzzle and a prize for the first to crack it. Here it is, pinned to the board. The limit, as n runs off to infinity, of the nth root of n factorial, divided by n(a) factorial, a root that changes with n, and a limit, all tangled together. What on earth does it settle down to? Think about the tug of war. N factorial is enormous, but you're taking its nth root and dividing by n as well. So does this crash to 0, climb to 1, or land on something stranger in between? Pause right here and lock in your guess. 0, 1, some odd number nobody expects. Say it out loud and drop it in the comments. A real detective always commits to a first theory. This one needs the master. Back by popular demand, the greatest detective of numbers who ever lived, Sir Isaac Newton.
Factorials again, Johnny, good. But look closer, this time they are not hiding a 9. They are hiding a number that runs through all of mathematics. The trick, as always, is to stop computing and start reading. Watch what one honest rewrite does. The nth root of n factorial over n is the nth root of n factorial divided by n to the n, and n to the n is just n multiplied by itself n times, so pair them up. 1 over n, 2 over n, 3 over n, all the way to n over n. And that expression has a name. The nth root of a product of n things is their geometric mean. So all we are really asking is this. Take the points 1 over n, 2 over n, up to 1, n little points marching evenly across the interval from 0 to 1. What is their geometric mean? As n grows, they fill the whole interval. So the whole monster collapses to one clean question. What is the geometric mean of all the numbers between 0 and 1? Now, a geometric mean loves logarithms, because the log of a product is a sum of logs. Take the log, and the geometric mean becomes an average of logarithms, the average of ln of 1 over n, ln of 2 over n, and so on. But an average of a function across an interval is exactly what an integral computes. This sum becomes the integral of ln x, from 0 to 1. Picture that integral as an area. The curve is y equals ln x between 0 and 1. Ln is negative. It dives down toward minus infinity near 0, yet the area it traps is perfectly finite, and that shaded signed area comes out to exactly minus 1. One tidy antiderivative confirms it. The integral of ln x is x ln x minus x plug in 1, and you get minus 1. The awkward end at 0 contributes nothing, because x ln x vanishes there. So the whole area is exactly minus 1.
Hold on, so the logarithm of our answer is exactly minus 1. Then the answer itself is
e to the minus 1, 1 over e, about 0.368. The scary factorial limit was quietly equal to 1 over Euler's number all along.
1 over e? Where did Euler's number even come from? There's no compound interest here, no circles, no growth, just factorials. That is wild.
Now 2 faster roads for the seasoned detective. The first uses Stirling's great approximation, a famous formula for n factorial. It says n factorial is roughly the square root of 2 pi n times the quantity n over e, all raised to the n. Stirling's formula is an adventure of its own, so we will give it a dedicated video very soon. For now, just watch what it does to our expression. Remember, we want the nth root of n factorial. And here is the key move. The nth root of a product is simply the product of the nth roots, so we may take the root of each piece on its own. Look at the main piece, n over e, raised to the n, its nth root is just n over e, the root and the power cancel perfectly. That is the whole engine. The leftover piece, the square root of 2 pi n, ends up raised to the tiny power 1 over 2n. And as n explodes, that power shrinks to 0, so the entire factor quietly slides down to 1. So after the dust settles, The nth root of n factorial is simply n over e divided by n. The n's cancel, and we land right back on 1 over e, the very same answer, reached by a completely different road. And the second road tells you exactly where e is hiding. Compare each term to the one before it, and the ratio becomes n over n plus 1, all raised to the n, which is 1 divided by the famous limit, 1 plus 1 over n, to the n. That limit is e itself. So e was baked in from the very start. So carve this into the notebook. A product too big to ever compute became an area you can find in one line. And here is the delightful part. The geometric mean of the numbers between 0 and 1 is not 1/2. It is 1 over e, about 0.368.
Now the surprise I promised. Here's your challenge, and it is a beautiful one. Take x raised to x raised to x raised to x forever, an infinite tower of powers. Suppose that whole endless tower equals 2. Your job, find x. Here's your one gentle hint, and it is the whole trick in disguise. Give the entire infinite tower a name, call it t. Now look at the very top. The exponent sitting on the first x is itself the same endless tower. So x to the power t equals t. Take it from there. Here's the deal. Post your answer in the comments with a short explanation of how you got it. The very first person with the correct solution wins a $5 gift voucher. My thank you for cracking it. Huge thanks to Sir Isaac Newton, and thank you for watching. If a little e just fell out of a factorial and made you smile, hit like and subscribe. Aha you in the next one.